Good morning, one and all Honors Physics students, to another episode of Honors Physics. It's Mr. Finn coming to you recorded, but not live, on March 27th, 2020. Hope you guys are well today. This is our last lesson before our scheduled spring break. So you guys will be off for a little bit of time. Videos will resume on the first Monday in April. And that will be our time to come back. I know we won't be in school at that particular time, but we will be online again. And I'll be moving into more of an electrostatic subject at that time. So we're going to wrap out sound and waves today and move on from our current topic. A couple of different announcements today, guys, other than videos resuming first Monday in April. But Google Form. The Google Form for today will be a review of the previous 2 weeks of material. So that will include the rest of waves and sound from before we left for the coronavirus outbreak. So that Google Form will be available today from about 10 a.m. to about 2 o'clock p.m. Make sure you get a chance to log on, complete the form as kind of a mini assessment, and just complete it right on Google Classroom, and I'll get it right back to you as soon as we're done. Okay, yesterday we talked a little bit about the speed of the airflow over the plane and the fact that there would be a reconciling of the velocity of that wind or that air movement as it got to the back of the plane. So this was part of the sonic boom that we were describing a couple of days ago. I want to make sure we address just that phenomenon about the airflow over the plane. It happens to be Bernoulis' law. And Bernoulis' law states that as the the velocity of a fluid is greater, the pressure is lower. And if the velocity of a fluid is lower, the pressure is greater. So it's best understood by me doing a quick demonstration with this piece of paper. So I've got just a small piece of paper here. You can see there's a little bit of writing on it. And I'm just going to let it hang down. So what I'm going to do is I'm going to blow over the top of the paper. And what that'll do is it's going to blow out the molecules in the top half of the paper, creating a low pressure zone. So the velocity of the airflow will be higher over the top of the paper. And subsequently, the pressure should be less, according to Bernoulis' principle. Consequently, though, the pressure on the lower half of the paper should rise in relation to the pressure over the top, because the airflow underneath is slow or not moving. So let's see if we can do this right. Ready? So you can see as I blew over the top of the paper actually rose up to be almost horizontal. Well, that's it, guys. That's basically Bernoulis' principle. Let's look at it in relation to the airplane wing from yesterday. Okay, guys. So let's talk about how this is going to work out in terms of the airplane wing. Number one, Bernoulis' principle, where the velocity of the fluid is high, pressure is low, and when the velocity of the fluid is low, the pressure is high. Just demonstrated that a minute ago. So here's my airplane. Now I do have air flowing faster, looks like underneath the plane if you take a look at that particular drawing. Over here is the idea that you have the actual silhouette of the wing. Well, long story short, you're going to need the velocity of that air to match up at the end of the wing. In other words, you're going to need the velocity of the wind over here to make up for the fact that it gets to this point and reconciles with this over on the side. So that's how the airflow over the wing relates to the demonstration you just saw, creating some pressure differences. And what we're going to see here Hopefully if you videoed that av.web video, you can see the actual rare refraction of the sound in the air. It's like waviness right around the wing patterns. So hopefully you can see that pretty well in that video. If you didn't get a chance to see that, go ahead and log into yesterday's video to check out the effects of the airflow over the wing and with the rear tail fin as well. Okay guys, let's wrap up for the whole unit then. Okay guys, we're back. Now, just a couple things to review before today's Google form and really the end of our unit. We didn't get a chance to do the speed of sound lab, which I do want to do, but I'm going to need to get back into the building to pick up a couple of things, maybe a couple extra forks, and give you some data online or through the videos so you can create those tables and maybe do a graph on that. So stay tuned for the Speed of Sound Lab, maybe after April 5th. But as far as topics go, what did we study over the last 2 weeks? We studied the speed of sound in air and different medium, like water, steel, warm air, dry air, and how the speed of sound is affected by its movement through materials according to bulk modulus on the numerator and density in the denominator. Remember, it was the square root of that quotient. Number 2, beat frequency. So two sounds sounded together, 282 hertz and 280 hertz. If they're sounded together, you're going to get an overriding beat frequency of about 2 hertz. Resonance, which we actually started the unit with the Tacoma Narrows Bridge and its collapse due to resonance, the forced vibration exactly matching the natural frequency of the bridge. Sonic booms. Sonic booms happen when an object is traveling at or near or above the speed of sound barrier and the waves can't get out of the way fast enough from being created in front. There's a great picture in your book about the front shock wave and the tail shock wave of a plane going by. So check out that for better details. Closed and open tubes, which is going to be the subject of our lab, closed tubes. And remember I did that with the bottles and then again with the tube of water. So check out that. And then of course the Doppler effect, the perceived change in frequency due to the motion of the source or the observer. So a lot of these things are molded together to make that sound section. Now as far as the wave section goes, we really just did a lot of conceptual stuff with waves and being able to use pendulums and springs to model how wave patterns are used. Remember, all waves have frequency and wavelength and amplitude. It's just a question of how we measure those things in the type of wave that we have. For example, wavelength for a light wave might be in nanometers, but amplitude might be in lumens. Amplitude for sound waves can be in decibels. Remember, we did talk about the decibel scale and how to convert and find intensity values from decibel values. Let's see. Making the wave from a spring going back and forth on a horizontal friction-free plane can be analogous to a ball moving around a circle. If you viewed that ball on a circle, on its edge, it can look very much like the spring on a horizontal friction-free plane. So I hope that helps, guys. We talked about all those things over the last few weeks. Some of it when we were in school, and then some of it when we were not in school. So hopefully you've got enough to work with there. I do want to touch base on one quick thing regarding an additional Doppler problem before I let you go today. So let's talk about that. Okay, guys, I got a quick problem for you. I have a bat flying toward a canyon wall or a cave wall, and he's flying at 3 meters per second. The bat emits a frequency of 500 hertz. Now, bats actually use sound to dictate their travel, so they know not to run into things because the frequency that they're getting is something that is bigger than the frequency they're emitting. So they're actually using the Doppler effect as a navigational tool. Pretty cool stuff. But anyway, 500 hertz of emission. Now what we're going to do is we can take this thing in two parts. You might be able to do it in one step, and that's fine. But I want to make sure we understand that there's actually two parts of the problem here. The first part would be the bat flying toward the cave wall. Now I have my picture of my bat here. I'm not a very good artist. So here's my bat flying toward the wall, emanating a sound of 500 hertz. That sound is going to reflect off the stationary wall and come back to the bat. So the wall is actually projecting the sound back to the bat. So the bat is both the observer and the source at the same time. So part one I have set up, bat flying to the wall. Well, here's my Doppler equation. F equals F sub 0, V plus V sub 0 over V minus V sub S. Now if I just put those numbers in, 500 hertz for the frequency of the bat, 343 on top, because the observer is not moving, I'm treating the wall as the observer. And 343 minus 3, because remember, V sub S is positive when approaching. The bat is approaching the wall. So that comes out to 504.4 hertz, by just sig figs, 504 hertz. Now, I'm going to take part two of the problem separately, but I'm going to use the 504 hertz as what's being projected off the wall back to the bat. So 504 times 343 plus 3, because this time the bat is the observer coming toward the wall, over 343 minus 0 because the wall is not moving. And you should get somewhere around 509 hertz. Now you could actually condense that into one step, and it would still work out. But sometimes it's easier when you're getting going just to take it into two different parts. So that's one example of where you might have the observer and the source be the exact same item. Instead of our example from the other day where we had Barney and Betsy, and one of them was the source and the other was the observer, and there was just a chase going on. I hope that helps, guys. If there's any questions, please get them in through email and I will address it on the next video. Okay guys, we're back. So, just to review, the Google form today is mostly going to be on sound, because that's the material we've been covering since we've been out of school. Doppler effect, speed of sound through different medium, speed of sound from bulk modulus and density, beat frequency, resonance, sonic booms, and of course closed and open tubes. I'm hoping that you guys will be okay with studying that material. We've been through a few questions here and there over the course of the week and a half that we've been together here online. So do your best and let's see how we go. And if there's any questions after that, email them in and I can address them after break when we come back on that first Monday in April. And you guys have been great, and I really appreciate all the subscribers and comments on my YouTube channel. Obviously, I apologize for the editing snafus that have come up in the early parts of me creating these videos, but I think I've got it down at least to a serviceable value, so you guys can rely on the fact that the editing won't chop out big parts of our content from here on forward. I apologize for that. And maybe over break I can look at those videos and maybe update them or delete the ones that are too chopped up. Anyway, thanks so much guys for tuning in, and we'll see you a little bit later this morning for our Google Meet session. And for all of you, those people outside on the outside who are not involved with physics class through this school, thanks so much for tuning in. And please comment, and I'll make sure I get back to you during my time away from making these videos, which is next week. We'll be back together again beginning April. Have a great day, guys. And